My name is Granger, and this is the gas turbine jet engine experiment. For first, a little bit of experimental objective is just using the engine configuration system to perform performance calculations using the first law of of energy conservation. So first law of thermodynamics for steady state, steady flow conditions. And this will be done for the compressor inlet, the whole Brayton cycle, which is part of the jet engine and the electric generator. And yeah, the electric generator. It's the first little experimental apparatus. It consists of two main parts. It's going to be your SR30 gas turbine. That's going to consist of your compressor, combustion, and then the turbine one. That's going to be your power turbine. And then the second is going to be the TG2000 turbo electric generator. That's going to consist of your power turbine and then the alternator. But yeah, each part is labeled and numbers associated in the raw data sheet for temperature and pressures. All right. And then for Brayton cycle calculations, so all of them are using ideal air conditions for steady state, steady flow. Enthalpy values were found using the interpolation for the given temperature values, and all that came from the air table of thermodynamics engineering approach 9th edition. Okay. So, and specific work for each device, and it's an open system. So, for the general little first law of thermodynamics, basically get the heat minus, yeah, the heat in minus the work is equal to the change in enthalpy. And then with kinetic energy and potential energy, if you basically make those negligible, you just get the equation down below. For actual example calculations, so the work from compressor, this is with steady state steady flow, we assume it's adiabatic. So it's just the work is that from heat and combustion, we assume no shaft work. So it's basically just the heat is equal to the change in enthalpy. And you see that everything on ideal conditions is based off a change in enthalpy, which is just basically what we're going to find with interpolation, as mentioned earlier. And then for the thermal efficiency that we need to find, it's net work over Qn. So that's just the work from the turbine minus the work for the compressor, and the Qn comes from the combustor. So then actual example calculations, you can see that we interpolated the values to find the H1, H3, H4, and H5. And then using Qn, or basically finding each part, we basically subtract, if you want to find it for the compressor inlet, it would just be H2 minus H1, as in that's the basically the exit minus the inlet of the device. So you would do that for the turbine, you'd do that for both power cycles turbine for the combustor as well. And then whenever we use the Qn, which is the minus from the compressor, minus the when it's the free range, because there's two turbines, one from the free range, the free turbine, and then one from the power. You add those together, subtracted by the compressor, we get a thermal efficiency of 37%. All right, for compressor inlet, compressor, mass flow rate of air, velocity, volumetric flow rate, and Mach number all need to be found. And we're basically going to use the inlet pressure and thermodynamics when we can find these values. So using energy balance, it's from our combustor basically. The Qn is the m dot fuel over the least heating value. And that Qn is going to be basically equal to the m dot air, which we need to find, times Cp T3 minus T2. Cp T3 minus T2 is also the same thing as enthalpy change. So that's just enthalpy H3 minus H2. But for this experiment, as stated earlier, I didn't have I didn't actually get to go through the procedure. So a lot of the things that I needed weren't here. So for some of these values, I assumed. So I needed to know the density of the m dot fuel. I needed to know the density or the least heating value, as well as the fuel used. So I basically assumed kind of like a jet fuel kerosene with a density of it was about 720 kilograms per meter squared. and the least heating value is about 33 kilojoules per kilogram. So you'll see in the calculations. Right. So then assuming that we can basically get the m dot air by setting, since we have everything, we can basically set m dot air by itself, get that. In order to find the velocity flow rate, that's basically the m dot air divided by the density. So that gives me velocity flow rate. Velocity flow rate is also equal to the area of the inlet that came from, well, I didn't see it on the lab manual. So I basically took the exact engine, which was the SR20, and found basically the impeller inlet of 100, basically around 100 millimeters. So with that area divided by, or that velocity divided by the area, that gives me I'm sorry, the volumetric flow rate divided by the area gives me the velocity. Then once I have velocity, I can find speed of the air in a sense, A, and that's based off of the K constant and R, which is just gas constants of air, able to find that Mach number of 0.2217, which that makes sense around, subsonic. Okay, so for the electrical generator analysis, this part of the analysis is purely graphical, where the graph basically asks you to make, well, I guess graph based off of lab data. So the first is just the N1 speed. That's going to be your actual gas turbine RPM, and that's basically speed versus time. And then your N2, which is the generator turbine, that's your speed and RPM versus time. So you see these here. And there was also fuel type versus time. Fuel type really did seem to have some issues. I think that data might have been botched. It was basically consistent around like 38 uh, liters per hour, and it just like fluctuated to zero at times. So there were some issues. More on that later. And then voltage versus time, and current versus time, and power versus time. All of these values are, well, they're not valually the same, but graphically they all look pretty similar and same shape. This is what the lab manual showed, that all of them had like very exact same shape. I think this is based off of one just power, voltage, and current basically all have an equation that link itself. Power is equal to voltage times current. So I believe that's why they have all similar shape. General issues with graph, with given data and fuel flow seem to have issues, like stated earlier, constant values really fluctuating from zero at times. Also, since the lab data was purely recorded and not, we actually didn't go through the procedure, I wasn't able to distinguish between certain time frames. So there is so no indication of load lever pinned, maximum excitation, and minimum excitation. So hypothetically, if I were to have those, what the lab manual was basically implying was purely just time marker. So it would basically just be have to written out during the procedure. So based off what the time marker actually is, I would just basically find the relevant value. So gas turbine, generator, speed ratio, which some of those require formulas, but the only ones that require formulas are those speed ratio, um, resistance, the P out, and the power specific fuel consumption. But the rest of those, it's literally just taking the time marker and then finding the value. But everything else is basically graphical. So it'd be that N2 minus N1, which come from the data. R using Ohm's law, it's just equal to voltage over I. That's those can be found from the data. The power out is literally just a phase three thing. So it's basically the root of three times voltage times current, which are all in power. And then the power specific fuel consumption, that in fuel from our combustion that was found earlier, would basically just be put over the P out that we just found. So yeah, that's everything. Here's my references.